Okay, in this video I'm going to show you an approximation technique for solving for concentrations at equilibrium called the 100 rule. First of all, I'm going to ignore the idea that I'm going to show you this technique and show you why it's necessary by looking at an equilibrium, and then we're going to come back and see how unsolvable that is and what we can do about that to make it a little better. So let's look at this equilibrium right here. Oh, I'm on eraser. Hold on. There we go. Okay, consider the equilibrium ammonia gas plus oxygen gas going to form nitrogen monoxide and water vapor. And we're going to say, just for the sake of a question, that we have half a molar concentration of both of the reactants at the beginning, and we want to know what the concentrations are at equilibrium. So let's imagine making an ice chart for this. We're going to have our ammonia gas, our oxygen gas, our nitrogen monoxide, and our water vapor. All of them need to be included because they're all variable concentrations. 0.5 molar for the start of those, and we're assuming that we have none of those at the beginning. And so the equilibrium has to shift to the right because it has to produce some sort of products. So this is going to go down by x. Hold on. See, that's why I want to put these coefficients on here so I don't forget to do that. So this is going to go down by 5x, or try again. Better go back to that eraser. There we go. Okay. Sorry, this is going to go down by 4x. This is going to go down by 5x. And these guys are going to get produced in ratio as well, plus 4x, plus 6x. And our new equilibrium concentrations will be 0.5 minus 4x, and 0.5 minus 5x, and 4x, and 6x. Now let's just see what happens when we stick this thing in the K expression. K is equal to the concentration of the products, nitrogen monoxide, to the exponent that was their coefficient, water, ammonia, and oxygen. Okay, now let's take these equilibrium expressions and insert them in the K expression. So 4x to the 4th, 6x to the 6th, 0.5 minus 4x to the 4th, and 0.5 minus 6x minus 5x. Oof, making a lot of silly mistakes here. 5x to the 5th. I don't need to go any further with this if we imagine, regardless of what the number is over here, that this is an expression to the power, the x's will be to the power 9 on the bottom, 4 plus 5, and to the 10 on the top, and it's going to make this gigantic 10th order polynomial. What I think you'll realize from your math class is it's not that hard to solve a linear. Quadratic's a little harder, but not that bad, and you can even maybe do it third order by now. A 10th order is totally out of the question. You're not solving it. If you had this, you're going to a computer. A computer will solve this for you, no problem. But if you don't want to use a computer to solve this equation, you're going to need some sort of approximation technique. Which brings us back to the 100 rule, which is what we're doing here. The 100 rule basically says if the conditions are right, this change of 4x and this change of 5x often are very, very small. And if they're very, very small, maybe they're going to be so small that we can ignore them. How can we check if they're going to be very, very small? Remember, K is the concentration of your products over the concentration of your reactants. So number one, to have very little change, we're going to want to have a lot of reactants and not very many products. If that's the case, that makes K very small. If K is small, we're going to have a lot of stuff sitting in the reactants. The forward reaction is going to be very weak, and maybe the amount of the reactants that get used up will be small enough that we can ignore them. That's not the only consideration, though. It really matters how much reactants we had in the first place. If we want to have a lot left over, then we should start in a situation where we have a lot. we can come up with one expression that combines those two ideas together. If the concentration of our reactants is big and the value for K is small, then reactants over K should lead to a large number, right? We've got a big number over a small number, so that so that should lead to something large. We need a benchmark here where we basically consider this ratio to be big enough to use this approximation technique. And the benchmark we're going to use is called the 100 rule. So if this is larger than 100, we're going to assume that these changes are small enough to be ignored. Now you might find in different textbooks or in different situations that this number, the 100 that they use, they might use a different number as their benchmark based on how careful they need to be with an approximation. Mr. McClure, for example, says that in university, they didn't call this the 100 rule, they called it the 500 rule because they wanted to be a little more accurate. In the end, with computers, we don't need to make the approximation at all, but it's still much easier to do so. So let's check our specific example here. Here we have a reactant concentration of 0.5 and a K value of 1.4 times 10 to the negative 14. So if I go 0.5 divided by 1 times 10 to the negative 14, I don't need to do the math here when I see that 10 to the negative 14, but just for the sake of it, I get 5 times 10 to the 13, which is big. In fact, it's much greater than 100. So what that means then is that I'm not getting very much products at all. I'm staying almost completely as reactants. In fact, I'm staying almost completely as reactants so much that I can neglect any change that happened to the reactants and treat the reactant concentrations as if they are constant throughout. What that means then is my K expression gets much simpler. It's still not great, but it's much better. If I can ignore the change to my reactant concentrations because I'm basically saying that that change is going to be small, then I get an expression here that's solvable. 1.4 times 10 to the negative 14 is going to be equal to 4x to the 4th times 6x to the 6th divided by 0.5 to the 9th. So this is solvable for x. Let's go ahead and do that. Let's see how big that change is, and let's see if we think that x was small enough that we could ignore it and we made a good approximation in this case. So 1.4 exponent negative 14 times 0.5 to the 9th gives me 2.73 times 10 to the negative 17, and 4 to the power 4 times 6 to the power 6 gives me 11,943,936. X to the 4 plus 6 is 10. Now solving both of these for x, I got 2.286 times 10 to the negative 24. And then putting that, or 10th rooting that, calculators are good things. I get 4.3 times 10 to the negative 3, or if you don't like scientific notation, 0.0043. I rounded that number a bit, but you get the idea. So now let's look at our concentrations at equilibrium. And I'm going to focus first on our reactants because I want to check if I feel still that this approximation was good. So I had ammonia. Ammonia started with a concentration of 0.5 molar, and I treated it as if it didn't change. But if I look at the expression and I don't make that cheat, I see that it should have decreased by 4x. So 0.5 minus 4 times 0.0043 is 0.48. So I guess you have to decide, are these two numbers close enough together that this change was insignificant? For the sake of how good chemistry measurements usually are, 0.5 and 0.48 are sort of close enough together that I would say that this approximation was pretty good in this situation. Let's look at the water. Was it water? I think it was water. Oh, no, it's not water, it's oxygen. It started at 0.5 and decreased by 5x? Yep, 5x. So 0.5 minus 5 times 0.0043. That's going to be equal to 0.5 minus 5 times 0.0043. 0.4785. Is that close enough to 0.5? Again, it's a little further away, but I would say it's pretty close. Our approximation is pretty good. What that means then is we don't need to go back and do anything else, unless we need the answer to be more accurate or really accurate for some specific reason in our experiment, and then we might need to go back and we could repeat this process or we could solve the problem with the computer. Okay, with all that in hand, we can go ahead and find our nitrogen monoxide and our water populations, or concentrations. Nitrogen monoxide was, I think, a 4x, and the other one's a 6x, which is 4 times our 0.0043, and 6 times our 0.0043, which gives us population, or concentrations, well, I keep saying population, 4 times 0.0043 of 0.0172 molar and 0.0258 molar. So they're pretty low. That's why the K value is low. So we have our two low things in comparison to our two high things. There was not much change then. So that's how we can use the 100 rule to give us an approximation for the concentrations at equilibrium without solving some monstrous equation. Again, if K is small, meaning there's very little products in comparison to the reactants, and the reactants start big, what we assume then is that the change to the reactants doesn't have to be that big to get to equilibrium. Not much of the forward reaction is going to happen. If we, as a benchmark, if we compare the concentration of the reactants to the K value and it's larger than 100, we can go ahead and make this approximation. What that means then is that my reactant population isn't going to change that much. So instead of this being 0.5 minus 4x, for the purposes of our calculation, we're going to ignore any change that occurred to it and treat it as if it was just 0.5. That's going to make our calculation solvable. And once our calculation is solvable, we can get x, and then we can plug x back into our original expressions to check if our approximation method was at least a little bit reasonable. If we said that the 0.5 wasn't going to change, so since the 0.5 only changed from 0.5 to 0.48, we're going to say that's pretty close to 0.5, so that's good enough. And then we can use that to find the new concentrations of both of our products which have been created. So that's the 100 rule.